I'm going to do now is I'm going to present my senior project in a PowerPoint. It's an abridged version of a Word document I happen to have here. I'm not going to read the Word document, it's just too much. But basically, what I've done was, since January when I started my senior project, was to research about nuclear chemistry and some of its uses in two major areas, in dating and nuclear medicine. So what I'm going to do is, I'm going to pull up this Microsoft PowerPoint, and then we're going to go through it. I'm just having this flip chart if I need to write anything. There's no question.
You can write on the PowerPoint.
Sorry? Yeah.
You can write on the PowerPoint too.
I'll do it from the computer. This is just view slideshow. Okay, so there's the opening. What we have to learn before we look at anything of nuclear chemistry is atomic theory. Now, the atom can be defined as the simplest unit of matter. For example, all of us here are made of atoms. You, the air you breathe, the food you eat, everything. And the atom itself is divided into further parts, the two being a positively charged nucleus and a negatively charged electron cloud. The word atom, this is just trivia. The word atom means that which is indivisible in Greek. And you can think of it as something that is basically infinitely small. For example, if you wanted to fill a sheet full of atoms, the thickness of a sheet, it would take you hundreds of thousands of them, I believe, to actually fill up the sheet. That's how small the atom is. But yeah, what else? Yeah, the atom, besides having a positively charged nucleus, usually has the neutrally charged particles called neutrons. I use blue here as a key. And yeah, most atoms, with some exceptions, seem to have just neutrons and protons. That's just a basic idea. You have the electrons that orbit around the atom, like in a manner analogous to the planets going around the sun. Yes, the concept of an element. When you look at substances like gold, silver, copper, iron, those are pure elements. And by that I mean a substance whose properties are defined by a specific atomic number or a number of protons. For example, here I have a few pictures I got from the internet. Gold over there has 79 protons. So that means that the atom that has, an atom has 79 protons is an atom of gold and only gold. That's what a chemical element can be defined as. You cannot break down gold into something else. Like you can break down water. Water is not an element. It's a chemical compound, for example. Yeah, and in order to identify elements most easily, we generally use a chemical symbol which relates to the name of the element. For example, I don't have it written here, but the symbol for gold is AU from its Latin name. That's right here too. Yeah. And bromine is Br, and copper is Cu. This goes on further, basically. Oh yeah. And we discussed that an atom is defined, an element is defined by the atomic number. Well, what happens is that a sample of an element can have different numbers of neutrons in its different atoms. That's called an isotope. For example, gold can have anywhere from 120, perhaps 125 neutrons, perhaps. And there's actually a way of identifying these isotopes by naming them. I'm going to go to that slide here. Okay, well, fine. Let's see the next slide. But this is the periodic table, see what you see here. And the main purpose of the periodic table is to arrange the elements so we can find these. I'm not going to go into much detail, but it goes like this. From left to right, it goes from increasing atomic number. So from hydrogen to helium, it's atomic number 1 and 2. Then from lithium to neon, it's 3 to 10, right? So I'm not going to go through every detail, but that's pretty much what you need to know. The periodic table is just a chart that is used for reference to keep track of the elements and so on. Here's what I was talking about earlier. In order to identify isotopes, we give them names, and by names, we identify the number of neutrons in terms of atomic mass. So let's look at iron here. This is an example. Iron is over here and it has 26 protons. But let us assume that we have an atom of iron with 34 neutrons in it. In order to write the symbol for it, we identify the entire mass of the nucleus, the atomic mass. That's the addition of the protons and the neutrons in the nucleus. So iron with 34 neutrons is called iron 60. You just do the math and you find out, oh, it has 34 neutrons in it. That's pretty much it. But what happens is that for historical purposes, some isotopes have specific names attached to them. For example, hydrogen-2 is sometimes called deuterium in chemical literature and physical literature. That's the same isotope that makes up heavy water. It's just for historical purposes, they're usually referred by their names, these names. And, I'm going to spend a little time with this, but when we measure the mass of an atom, we don't use kilograms or pounds or anything like that. It's just, the mass is just so small, we prefer to use another unit called the atomic mass unit. And it's defined as the 1/12 the mass of carbon-12 atoms. So, because of that definition, carbon-12 has a mass of 12 atomic units exactly. And here, I wrote this down so it gives you to have an idea how small an AMU can really be. 1.66 to the power of negative 27 kilograms. So that's pretty much, it's 1.66 with 26 zeros before. That gives you an idea how small it truly is. And I want to sum up this paragraph, which is pretty interesting. The mass of an element, a naturally occurring element, is not the mass of a single isotope, because most elements do not exist as single isotopes in nature. So if you were to look at a periodic table, let's look at it here. For example, strontium. It's not a perfect number. It's 87.62 AMU. The reason why is because it can exist as mixtures of isotopes. And we find the average atomic mass of this isotope here. What they usually do is they come up with a percent abundance of the isotopes of that element. They multiply its decimal form by the atomic mass, and then they come up with the eventual average atomic mass for that element. Unless you're doing experiments with specific isotopes, we generally just assume that a naturally occurring element has the same atomic mass as given. I'm going to skip these two slides. Okay, now we get into the part of radioactivity. Radioactivity may be defined as the breakdown of an unstable nucleus. When you hear the words alpha particles, beta particles, or radiation, that's because a nucleus is breaking down. This is a change in the nucleus. Now, one explanation for why elements tend to be radioactive is due to the atomic number. There are two forces that are working in the nucleus. First off, the electromagnetic force, which would normally repel the allied charges of the protons. Now, the reason as to why the protons do go flying off from the nucleus is because there's another force that acts on it. That force is the strong force, which causes the protons and the entire nucleus as a whole to coalesce. Now, what an explanation for this radioactivity is that as the atomic number continues to increase and increase, this electromagnetic force eventually overcomes the strong force and allows the protons to repel each other and cause the nucleus to become unstable. C-lead, let us go all the way over here with the atomic number 82. What's been found is that all elements that become heavier than lead, everything all the way over here, is inherently radioactive. So metals like uranium, plutonium, all of them are inherently radioactive because they are heavier than lead, because the electromagnetic force has overcome the strong force in the nucleus. And actually here you have basically anything heavier than lead is inherently radioactive. And I'm going to go to the next slide. This is what I want to get to. There are are different ways by which a nucleus changes into another nucleus. And the first one discussed here is alpha radiation or alpha decay. This is usually characteristic of very heavy elements, like anything heavier than polonium or uranium, thorium, so on. All these elements here generally go by alpha decay. In alpha decay, the given nucleus expels a nucleus of helium-4. What this means is that the element loses 2 protons and becomes the element that is 2 protons lighter than it. So, for example, uranium here with 92 protons goes through alpha decay. What that means is that it becomes thorium. It has 90 protons, so just do that together. And at the same time, it loses 2 neutrons. Think of it, the mass of helium-4. So I'm going to give you an example I know by memory. Uranium-238. It goes through alpha, decayed by alpha decay, so it becomes thorium-234. The atomic mass, in summary, goes down by 4, and the atomic number goes down by 2. Yeah, that's good. The second part is a very different one called beta decay. In this case, electrons or their counterparts, the positrons, are involved. There are 3 different forms of beta decay illustrated over here. First one is, the example is oxygen. See, these happen usually like nuclei, like oxygen, lithium, these generally do not go to nuclei. It's more favorable to these nuclei. One of the forms of beta decay, which is shown here, beta plus, yields an electron with a positive charge. And what happens in it is that the atomic number goes down by 1. So in this case, oxygen with 8 protons becomes nitrogen, which has 7 protons. And the second one yields the electron we're all familiar with, an electron with a negative charge. Carbon-14, which has 6 protons, it becomes nitrogen with 7 protons. So it becomes the following element. And that's the third one. That's called electron capture. What happens is that the nucleus actually absorbs an electron from the outer cloud, and it becomes the following element, preceding element, sorry. In this case, from aluminum to magnesium. I think that's pretty much it. Oh, there, yeah, this is a short paragraph. There's a third force involved here called the weak nuclear force. This is basically the only major state it's involved in. The weak nuclear force is majorly involved with beta decay in this case. I think I'm going to skip this part. I can do this. Okay, yeah, this is. Now, what this is basically telling you is that if we have a measurable amount of a substance, like in grams of a reactive substance, it decreases exponentially as shown in this graph down here. Now, what this means is that after some time, half of that substance has decayed away, exactly half. The time that it takes for that to happen is called the half-life of that substance. It could number from anywhere to seconds to billions of years. That's why the uranium that was here from the Earth form is still here. It has such a long half-life, but it hasn't decayed completely yet. They use this equation here. Basically, it relates the amount of substance to the half-life and time elapsed. Here it is. This is the part I was talking to you about. We're going to start here with the part of radiometric dating. And you can basically define radiometric dating as the use of radioactive substances to estimate the age of usually old, very old objects like minerals, pottery, remains, and so on. Here, this paragraph basically using two examples of isotopes used in dating. The first one being uranium-238, which I already mentioned. Because of its long half-life, uranium can be used to date the oldest minerals and rocks on the Earth, for example, due to its long half-life. But here we have a second example, carbon-14. It has a half-life of 5,730 years. So the big difference here is that a short-lived element like carbon-14 is generally used for something that is up to 60,000 years old. So if you ever hear a report of a dinosaur bone being dated by carbon-14, that's not possible. It's just too old to have any carbon left, since most of it has already decayed. So that's one of the things you have to know what you're dating and the context of what you're dating, so you know what to use. You can't. If something is too young, like something like a few years old, like 10 years old, you can't use uranium to date it. Not enough of it has decayed away to notice any change in it. We're going to look at next are specific dating methods. First one is uranium lead dating. What uranium does is that in order to reach a stable isotope, it decays through many events, eventually forming lead in its decay series. What the graph here shows is how the different elements it goes through before it finally forms stable lead. And the thing is, there are two isotopes of uranium used here: uranium-235 and uranium-238. Both of them are long-lived enough so that we can date the oldest rocks that are on the Earth. And that's a good thing. And the other good thing is that because there are two decay series associated with uranium dating, we can use it as a cross-check for the age that we get. One of the favorite minerals of geologists is called zircon, which is right here. This is brown material. The good thing is that this specific material is inert, so it's difficult for any lead or uranium to get out, so it doesn't really distort the age of the sample. Here's carbon-14 that I was mentioning earlier. Carbon-14 is solely used for young remains, like I said before, 60,000 years old, no older than that. And it's usually performed with organic remains like bodies or even the dead sea scrolls that we found in the 1940s. The thing is that all of us here can have carbon-14 at any given point. It exists in nature by known trace quantities. See, when an organism dies, it no longer takes in new carbon from the atmosphere. It doesn't go through photosynthesis, doesn't eat, doesn't breathe or anything. And that means that as time goes by, the carbon-14 ratio decreases continually. And if we were to examine this ratio of stable carbon to carbon-14, we can estimate the age of when this organism died, or when this was deposited. What happens is that there are some times that the carbon-14 ratio in the atmosphere can change, like usually to volcanic eruptions or usually because of volcanic eruptions. But even if that's true, scientists are aware of this change in the amount of carbon-14 in the atmosphere, so that's not really an issue. They can calibrate it and look at how the ratio stable to reactive carbon has changed. So there's no big issue with that. This has been known since the 50s, so now we've been able to work out this problem. So potassium-argon dating is based on the beta decay of potassium into argon. Basically, like uranium, has a very long half-life with respect to the age of the Earth. So we can use to date just anything from the Earth's formation. And basically what they do is that they usually take a part of the mineral being dated and they grind it up, and usually in solution they like take a minuscule amount of it and they pass it through. They measure the amount of argon to stable argon, and by knowing that ratio, they can actually determine the age to much the accuracy actually. They use an acid here to dissolve it actually, hydrofluoric acid. And usually they perform it on common minerals such as feldspar, granite, and so on. I'm going to go through this one actually. That's one. This one I'm going to go through. This one actually does not use any decay in it per se. What it uses is actually the damage on crystal lattices of objects. A heavy isotope like uranium-238 that can break up into larger atoms, like usually atoms are usually this heavy, not necessarily alpha particles. And when it does that, the fission fragment actually can cause damage to the crystalline lattice. And as you can see here, they're big enough so they can be seen with a microscope. And by counting the fission events or fission damage done by the uranium, they can estimate how long ago this reaction started. And the good thing about this is that even if it has uranium, which has a long half-life, they can still use it to date recent artifacts because it doesn't depend on the amount of uranium, but rather the damage it causes to the object. This is the source we're going to use from. I think we skip this one actually. Okay, this is our which we start with nuclear medicine. The first part of this is going to be on the PET scan, and the later parts of the project are dedicated to specific nuclides that are used, such as imaging or dealing with cancer problems. Yeah, there's also this part with radiation damage, but I'm going to go through it very quickly. When you're bombarded by something like alpha particles, beta particles, or gamma rays, the reason as to why it causes damage is mostly because the energy from the radiation disrupts the chemistry of the body by damaging the molecules. This is specifically dangerous because our body depends on the chemistry of cells and so on. So it eventually can attack DNA. By attacking DNA, it can distort the entire structure of DNA and cause cancer, basically, because of this genetic damage, especially the cells in a tumor out of Here I have the word free radical, and by that I mean a free radical is basically a molecule that's highly reactive. And these highly reactive molecules are produced by ionization. Even something so small as a water molecule can still become dangerous if it reacts with the DNA. That's basically the damage that causes cancer. Next section kind of deals with measuring radiation damage by okay, here's the so what this really uses is a beta emitting particle. What happens is that the beta emitting particle usually yields a positively charged electron, like I showed you before. And it's not long before the positively charged electron meets a standard electron. And what happens is that they annihilate each other. When this annihilation happens, it yields gamma rays. Now, the PET scan has a camera in it that can detect these gamma rays and convert them to an actual electric pulse. So it forms the image from the effects of gamma rays. So, if we put, a beta emitting particle in the brain, with small gamma rays, we can actually get an image of the brain. That's pretty much how we get the image. Now the PET scan is a small image here. What they do is that they ask the patient to lie down on a bed, and they keep the patients like we pass into a machine that has the cameras, the measuring cameras, and that's how they get it usually. This one here is called fluorine 18, and what they do with fluorine 18 is that they use it to fight against cancerous cells usually. For example, they put it into a glucose-like molecule called fluorine FDG. And because it's chemically similar to glucose, the cells can uptake it as if it were just standard glucose, no difference whatsoever. And the thing is, because cancerous cells have such a strong affinity for glucose, they basically absorb this as if it were nothing different. And that's why they can use it to image cancerous cells. If cancerous cells and normal cells were to take up the same amount of glucose, it would be useless to try to image it. Here, what they usually ask of a patient who's taking this glucose-like molecules that they rest for almost 6 hours, and then so that it allows for the compound to pass easily into the bloodstream. So, this other molecule here is phosphorus 32. What they do is that they inject this radioactive form of phosphorus in the form of a compound, which is a chromium-bearing salt, phosphate. And the thing is that the phosphate, the chromium, is widely used as an energy source for cells. And usually cancerous cells, like I said before, have a higher affinity for energy-bearing molecules. In this case, here, any one of these phosphorus atoms are in the molecule would be radioactive phosphorus. That's pretty much the whole story behind it. But the thing is, I read here from one of my sources that actually phosphorus 32 may be a bit unsafe because it's been shown to cause leukemia in young children. Yeah, the only source I have here showing that. And usually it's used to treat ovarian, lung, and uterine and prostate cancer. That one over there is a drawing relates to cobalt 60. Cobalt 60 is notoriously good gamma radiation emitter. So what they usually do is they use this teletherapy machine where they put a cobalt source. Now they aim the gamma rays of the cobalt at some area, in this case the chest. So if there's a cancer in the chest, they can actually use the gamma ray beam from the cobalt and actually fight against the cancer that's over there. And that's it for cobalt 60 basically. And this one here is called technetium 99M. What happens is that this M means that the nucleus of this technetium yields gamma rays. It's energetically excited. So the good thing is that they put in a compound form, they usually allow it to travel to the heart. It has an affinity for the heart muscle. And that's why it's so good at imaging the heart. It's this affinity that helps it to get over it. And what they do in this case is they perform something called a stress test. In order to get the heart active and to start uptaking it, they ask the patient to usually walk on a treadmill. My brother-in-law had this done, so I heard of this. They usually ask the patient to walk on a treadmill for some time so that the molecule gets there. And yeah, that's pretty much it. Okay. And here's a good thing. If assuming that the heart is healthy, there should be no problem with the molecule getting there. See, this is why it's good. Now that if it accumulates after some time, we know that the heart is relatively healthy. Another isotope I don't discuss here that's also used is called thallium-201. Apparently it's mostly being, it's apparently has the same use as this one, but this is very much a major one I discussed here. But I told you already that my brother-in-law had a stress test done. So that's how I actually found out about this. And I started researching it. Okay, there's two more there. Here is iodine 131. Now the thing is, this, the iodine, the element, is usually taken in by the thyroid over here. It's used to make hormones, and the thing is, this affinity is what makes iodine 131 very good for fighting thyroid cancer. See, this gamma ray emitting isotope travels into the thyroid in chemical form, usually with sodium iodide with pills, and that's how they get it to go over there and fight cancer. Eventually, you know, the gamma rays are spewed by the isotope simply help to fight against cancer. And here I put a fun fact over there. Although iodine 131 is used in medicine, there have been incidents where iodine 131 from nuclear tests has actually made its way to the food chain. Usually it was carried by the winds, and sometimes it made its way to vegetation and even milk. It's been shown that people who were in their teens and the 50s to 60s are actually at a higher risk of thyroid cancer, especially in areas where the nuclear tests. There have been even compensations for that, if it's been proven that thyroid cancer was caused as a result of that. And this one over here, this is a very interesting one. It's actually iridium, a metal that is inserted in a pill form into the body. Now what they actually do here, called brachytherapy, they insert a tablet made of iridium and they allow it to stay in a region, usually breast cancer. They usually to fight breast cancer, they insert it there surgically and allow it to yield its gamma rays to fight the cancerous cells. So, but they don't give you pure uridium actually. They usually alloy it with other chemically inert metals just to make sure it's not affected by the cancer in the body. So here there's usually tablets, usually what they and that's not the deal. I know it's not professionally made, but most of these are websites and some of these are most of the school that I got. That's some of the parts I decided to skip because I thought that they were, you know, too central to what I was discussing. I skipped the part of radiation, the electromagnetic radiation over here. I skipped that part because I thought it would, you know, kind of not get in the way of understanding what I was discussing. So that's the abridged version of the Word document that I wrote for my project. It's over here, as you can see. Yeah, that's where I worked on the scholarship project.
Good job.
Some of you have to go also.
Any
If you
questions?
want to, I know I didn't have a copy of this for you, but if you want to have a copy of my little just over there.
No questions?
This PowerPoint just send it.
The cast one is in lung cancer. Like very isotopes in the
Here, I got actually. I have a question for you. Most of the anti-cancer therapies, is there a pattern in that they are all gamma emitters or they are all beta emitters, or is there a pattern to what kind of emission tends to be?
Usually, gamma ray emitters are best for fighting cancer, like cobalt-60. And beta emitters are usually used for the imaging process in the PET scan. Is that what you're looking for?
Why is that? Do you have an idea?
Sorry?
Do you have an idea why that might be?
Because when the positively charged particle that is emitted by usually the beta emitter collides with an electron from the surrounding matter, it forms gamma rays. Gamma rays are what actually are the source of the image. There are cameras built into a PET scanner that can detect the gamma radiation and turn it into a visible image like I showed you over here. Let me show you. But basically that's it. It's the annihilation between the two particles which yields gamma rays as the source of this imaging process. Without it, well, we wouldn't have it.
Yeah.
Any other questions?
With all the research that you did, the paper that you wrote, the PowerPoint that you created, what, do you have any plans of what you're gonna be doing with that? Is that something that you're gonna be using in the future? Is that something that you would like to get published, or?
Well, I think I'll keep it as a reference to writing. You see, I think that writing this has helped me to at least learn to put effort into a major project. So I would think what I'm going to do is I'm going to keep all of this close to me, including what I'm filming right now, and, you know, keep it as a guide, for especially if I'm going to perhaps get a job at teaching, because that's what I'm planning. See, I think Dr. Walker suggested that I actually make the PowerPoint. I'm going to be serious. You see, if I had actually read to you